name is Shmuela Jacobs. I'm from the Technion, from the ESML lab, and I'm going to talk today about my master's thesis, at least a part of it, about visual models and their representation in the semantic web. We're talking about two-way translation of OPM models to and from RDF format. The whole idea is about model-based system engineering, how to make it better. We now see that more and more systems get so complicated, and models are a very good way to keep the people involved, to let them understand what's going on in the system and to make changes. And this method is becoming more and more used and common in the industry and in research. Now, one of the problems in model-based systems engineering is that there are many different kinds of models, and different teams that work on the same system often use different models and different tools to represent the same things, but these tools are not integrated one with the other. So many times they may talk about the same element, but give it a different name, and they actually don't know that it's the same element, and they can't update instantly. If there's an update in one model, then they have to find the same element in the other model and update it. And this problem causes many frustration, a lot of frustration. And before we go to the solution, I'll introduce OPM, Object Process Methodology, which is a methodology of modeling systems that we work with and in our lab. It is a holistic methodology which shows all the parts of the system, what it's constructed of, and the processes that are done in the system. It is really intuitive and simple to learn, so we recommend using it, especially in the first stages of the system architecture and design. We'll see more about the OPM in this lecture. So I talked about the problem. So we have different modeling languages. One of them is OPM. Another may be SysML, as we can see in this slide. There are many other different modeling languages. And in IBM Research and Development Center, they construct a system, a platform for integrating models in different languages, and their system is called SMC, Semantic Mediation Container, and it contains ontologies of the different modeling languages, and it contains also rules for translating from one language to another. And the ontologies and rules are written in OWL, which is Web Ontology Language. And all the files, also the ontologies, all the files are in RDF format, Resource Description Framework, which is a framework for the semantic web, for representing data on the web and using it and searching this data and sending it from one tool to another, from one web server to another server. It becomes more and more popular today, so in IBM they decided to work with this format, and this will be the common language for all the models. But still, it is not a real common language, it's just a common format, and the language itself is defined in the ontologies. Now, if we want to have OPM in the SMC system, which means that we want to translate OPM models to other languages and from other languages to OPM, we have to work with to develop our tool, OPCAT, which is the modeling tool for OPM, and add modules to it to allow us to import models from RDF format to OPCAT and export models from OPCAT to RDF format, all according to the OPM ontology that we've defined. And as a result, we will have OPM models represented in RDF format that are either created from OPCAT or created in SMC and imported into OPCAT. The tools that we used for the research are Protege for defining the model, the ontology of OPM, OPCAT, the OPM modeling tool, which is written in Java, and we've added modules in Java to it, and Apache Gina, which is a library for using RDF files and models. So here we have a model of the process of the research, OPM mediation preparing. So I won't walk through the whole model, but the first process that we need to do is to define the OPM ontology. So to define an ontology of anything, we need to see what it contains, what kind of language do we use, what words are used in this context. So to do this, we will open OPCAT and see what it has to show us when we look at an OPM model. So we have, you can see in the bottom, we have different elements, OPM elements. The three on the left are the basic elements of object, process, and state that objects can have. And all the other triangles and links are relations. So we can see in the model on the top that we use the objects, some with or without states, and we see the processes, and they are connected one to another. We can see that elements have position. It is a graphical model, graphical representation of the model. So we need to think about the position of the element, and does it have any semantic in the OPM world? In our case, there is semantics, some semantics to the positioning of the elements. If we look at the process that is marked in the middle, tool request gesturing, it is shown inside the big process tool requesting. It means that tool requesting contains the process tool request gesturing and the other three processes that you can see also. So here we have the relative positioning of one ellipse inside another ellipse, or it can be an object, a rectangle inside the ellipse. Then the ellipse, the process, contains this object also. And we have another element of positioning that we have to consider. And the processes, the sub-processes, which are inside the big one, are ordered from top to bottom. And this is their execution order. So if we look at this, the process tool requesting, the first sub-process that will happen will be request modality selecting, and after it finishes, we go on to tool request uttering, and then to the third process and the fourth one. So we can see that some visual elements are really important here in the model. Unlike other modeling languages where usually it doesn't matter where you put an element, as long as it has a certain name or connected with a link to something. Here in OPM we do have the semantics here for the positioning, for the visual representation. Okay, let's see what else we have here. We have a hierarchy of the model, which is built by zooming into the processes. So here we can see the diagram that shows the zoomed in process tool requesting. So we zoom into it and we can see its sub-processes. And each sub-processes, we can zoom into it even more, or we can zoom out until we get to the highest process in the hierarchy, which is one process that defines our whole system, what the system does. So we need to think whether to include the hierarchy data also in the RDF, in the semantic web format, or is it not important all of the times? Now, some of the hierarchy is really created because we zoom into processes, meaning a process that includes other sub-processes immediately creates a part of the hierarchy. So maybe we don't need to save the hierarchy data as itself. The same way, we don't really need to save the coordinates of the elements in the model, because it's not really useful for other purposes, for other modeling tools. But we can rebuild some of the hierarchy back if we know which process contains other processes. Also, some of the hierarchy is created also by objects that contain other objects and so on. We're talking about how we're linking all of it to RDF, Resource Description Framework. So let's talk a little bit about what we have in RDF. We have resources. So for example, resources can be actual things that we can tell something about them. Snacks preparing, snack. OPM process is also a resource. It's a resource that tells us that there's a type of something. And OPM object is also a type, so it's a resource. Resources can be linked one to another by properties. And here we can see three object properties, which means that the subject and object are both resources or resources of RDF. So snack preparing is of type OPM process. Snacks preparing yields snack, and snack is of type OPM object. We can also have data properties where the object is not a resource, but a more primitive element like number, date, string, and so on. But it can't be a subject of another property. So here we can see that the snacks preparing has a property of duration, and the duration is 5 minutes. All these elements together create triples of subject, property, and object. So we can see here one triple, another one, 4 triples in this small RDF model. Now, how do we show OPM elements, OPM data in an RDF format. How do we take this whole complex model, all this complex data, and flatten it to simple triples? So here, for example, we have an in-zoomed process, and so the first relation that we have is that the big process, the in-zoomed process, contains all the elements that are inside it. Another thing that we want to know, to preserve in RDF format, is the position or the relative position of the processes, which is the relative order of execution. So we need to have properties to tell us which process is before or after another, and which processes occur in parallel. And then we also need to think about the representation of links. Can it be a simple representation, just one triple, as we saw before, snacks preparing yield snack, or do we need to preserve more data? For example, if it yields more than one snack, which means this link has cardinality, where do we save this data? So there are some methods that we considered in representing links. In the end, we decided that links are also resources because they have some data that is related only to them and not to the object or the subject alone. For example, the cardinality. Okay, so in the end, we have three parts for the ontology. One is the classes, which is the types of resources that we may have in an OPM model. We are using here inheritance between the different classes, not only the classes, between everything in the ontology. So here we represent the object properties. For example, the contains property, that one process may contain another process. And we have also some data properties, like you see a cardinality or a maximum time activation and so on. Okay, now that we have defined the ontology, we can export the data from an OPM model to the RDF format. I have here the algorithm for exporting, but well, we won't dwell into it. The third process that we need to do now that we have OPM models in RDF format, then we can import them back to OPCAT and see whether the result is satisfactory, and make improvements to the ontology. But we have some problems. I'm sorry? Someone talking? Okay. Okay, so some problems, that data is missing. Like we said before, we have visual models, and we don't save all the visual data in the RDF model. So we don't have the elements coordinates, and we don't have the full hierarchy. Now, we presume that the user will adjust the layout manually, but we need to give an option for at least seeing which elements there are, and let them be on the screen in an obvious visual way, so that the user will not miss them. We also assume that the model that we have is correct and complete. For example, if we have a link, then we know which two elements are linked to it in both ends. This data might be missing when we import a model, because we don't always control what we have in the RDF format of the model. Because it comes from translating the model from another language, for example. Okay, so we have here an algorithm for importing the RDF model into OPCAT, but I'll show it in a visual way. As an example, we have the moon exploring system. And here we can see the hierarchy of the original model and the converted model, which means after we translated the model, the original model, to RDF and imported it back, we can see that the hierarchy is slightly different. We still have four diagrams which represent processes inzoomed more and more, and the last diagram, SD2, is a diagram of spacecraft unfolded, which means it's not an in-zoom of a process, but it's it's showing the structural links of the spacecraft. So we'll see it here in the models. On the left side in pink, this is the original model, and on the right side, we see the stages of importing the model back from the RDF format into OPCAT. So we see that the basic elements are there. The process and the objects that are linked to it are there in the result, but we also have some more objects that are linked to spacecraft, which this data probably came from the last diagram that we saw in the hierarchy that is missing in the imported model. So here we see the in-zoomed process, and we can see that in the importing process, the sub-processes are aligned in the position one underneath the other in the same way that they were positioned in the original model. Now pay attention that the position on the x-axis, on the horizontal axis, is not really important. There is no semantics to that. There is only semantics to the position on the vertical axis. So the processes may have moved horizontally, but as long as the order is preserved in the vertical axis, then it is okay. So you see that first what the processes that the main process contains and an object that it also contains are imported, and then links are added between the processes and other objects that are important together with these links. And then last, the more objects are added which are linked with structural links to other objects and not to processes. And we do this cycle a few times until there are no more links to import. So here's another example where we have two parallel processes in the two first sub-processes which are in the same height level are parallel, and this is preserved also when we import the model back. So here we have structural links between one process and its sub-processes, and also these structural links are preserved. And finally, the last diagram that did not appear in the hierarchy of the imported model, we can see that all the elements and all the links in this diagram appear in two different diagrams in the imported model, in the converted model. So the data is preserved, but it's shown in different diagrams. Now, this is another slide showing just that. Now, we evaluated this work in two ways. First is by comparing the OPL. OPL is Object Process Language. It means that every element that we have, especially every link that we have in the model, there is a sentence in English that is constructed automatically, which represents it. So we can compare the sentences that we got in the original model and the sentences in the converted model. And if the data is preserved, then we must find each sentences that was before. We must find it also in the after, in the converted model. Now, another method for evaluation was using OPM experts. These experts received two models. Each model, they received it in two representations, the original one and the converted one. So first they had the blue model, blue model of the dishwasher model, and one of the CT scanner model. They saw these models, answered questions about them, and then they received the same model but in the other representation. So if the blue model was the original dishwasher model, then the green one was the converted one, and the other way around with the CT scanner model. First they got the converted model, and only afterwards they had the original one. And now once they moved from blue to green, they couldn't go back to change their answers. And the questions were the same questions for both colors. Now we saw that most of the questions were answered correctly, meaning the data is preserved when converting a model from the original to the imported one after translating it to RDF. So we had no significant statistical differences between the grades of the two models, meaning they were the same difficulty level. There were some differences which do not, when we investigated the differences, we saw that they do not concern the translation process specifically, but they concern the visualization of the data. So I'll go back to one of the models that we see. So here, for example, we can see structural links between objects, and the structural link may appear in this diagram or maybe in some other diagram, but as long as there is a structural link between two objects, then it means that the two objects are related to each other, and it doesn't matter in which diagram we can see this. But when you look at one diagram and you search for information and this link does not appear there, then you might think that the objects are not linked. For example, here in the original model, you can see in the top process, a spacecraft is linked, actually contains spaceship, but in the converted model, we have the same spacecraft, and we have the object spaceship also in the same diagram, but they are not linked here. They are linked in some other diagram. So the data is there, but not in the same diagram. So if I'd like to know what are the objects that the spacecraft is constructed of, composed of, and look only at this diagram, then I might think that it is not composed of spaceship, which is wrong. So this was a problem that we saw in the evaluation by experts, but this problem wasn't specific to the imported model. They had the same problem. They answered one question wrongly, looking at the original model, which means that we have to think a little more about where we present the data so that it will be easy to understand it and to have the whole picture, but also not too much of the picture, because one of the things that might be mostly confusing is having too much data in one diagram. So we have the next step is to define rules for translation between OPM and other modeling languages, but we haven't got to this stage yet. And we have a lot of ideas for future work. So some ideas for future work. So some of the future work involves the visualization of data and how we can show more data in a diagram, but without getting it too crowded. And representing OPM in RDF format, which is the format of the semantic web, is not it's not supposed to be only for the purpose of integrating OPM into SMC, to IBM system. It started this way, but once you have a model written in a format that any computer around the world that is linked to the web may take and process, then you have many different things that you can do with it. And one of the ideas that we think about is having OPM models of actual things that will be linked to the Internet of Things. For example, you may control your air conditioner at home while you're at work using the Internet, or maybe your refrigerator, and maybe moving things around or clicking on a process or an object. So we have many ideas for that, and we're very excited about the opportunities that this work has opened for us and for OPM. I would like to thank the Visionair project, which this research was partially supported by. And I would like to also thank the team members in IBM who helped me with this project.